Okay, it's time to start our next video. Okay, great. Oops. I always do that by mistake on these things. Better get some focus again now. Okay, so aren't these devices wonderful? Yahoo. Anyway, our next section is about 4.2, area. It's about area, which is 4.2. Okay? Well, let's see. What's there to talk about area? I mean, if you have a rectangle with length L and width W, then the area is length times width. What's there to talk about? I mean, if you have a triangle where the height is h and the base is b, then of course the area is 1/2 base times height. What else? Or if you have a circle and the radius is r, then the area is pi r squared. I mean, what else is there to talk about area, man? Well, what if you were trying to find this type of area? Okay? What if you had a function, say like this, and say the function looked like this, and you were looking at it only over a closed interval, and you just wanted to know, what is this area in here? Well, let's see, if it's a rectangle, it's just length times width. But wait a minute, that's not a rectangle. Well, if it's a triangle, it's just 1/2 base times height. Well, look carefully. It's not a triangle. Well, if it's a circle, it's just pi r squared. Well, look, it's not a circle. It's some kind of wedge-shaped figure. So suddenly it seems like area, indeed, is quite complicated. How on earth would you find the area under this function? It's not one of our usual shapes. Well, remarkably, Newton found a way to, and it's really quite childish. Okay, since we know the area of a rectangle, his idea was to fill this with rectangles. Okay, since we know the area of the rectangles, we could at least find their areas and add their areas up. Okay? So I'm just going to draw a curve. Forget about the x and y axes. I'm just going to draw a curve for a minute. Here's a curve. If I put just two rectangles under it, it would look like this. So you can see the area of these two rectangles, of which I know, length times width, give too much area. You see, I'm getting too much. I'm not just getting the stuff under the curve. But I'm going to draw that same curve and put 3 rectangles under there. So if I put 3 rectangles in there, indeed I don't get the area, I get too much again, but I get less too much than before. And indeed, if I put a whole bunch of rectangles under there, you can barely see how much I'm getting too much of. I'm still getting too much area. Yeah? But it's getting better the more rectangles I put underneath the function. Yeah, so the estimate gets better. So the real area underneath this curve or function will be a limit of me doing this, a limit of me doing this infinitely often, putting infinitely many rectangles under here. Not 2, not 3, not 10, but a million. Nah. A billion. Nah. A trillion. I'd have to let the number of rectangles go towards infinity. Then it will converge to the area, because the estimate keeps missing less and less. Yeah? Notice I've used the left-hand endpoint to be the how tall each rectangle is. Notice all the dots are on the left. Well, you could do it when they're all on the right, too. Like if this was a curve, then your first box would look like that. Second box would look like that. Yeah? And you can see now you have too little. Yeah, you're now less than the area. And if you put 3 in there, again, first box would look like that. Second box would look like that. Third box would look like that. Okay? Again, you're less than the real area. Okay? And finally, if I put a whole bunch of boxes in there, you're really close to the area. Still not equal to the area, but you're closer than before. Because you're missing even less. Okay? So again, the estimate gets better. Now notice that this estimate here for this picture is an overestimate. Yeah? Because I'm getting too much area. My boxes cover more area than what's under the curve. Notice in this picture down here, they cover less. You see I'm missing some of this area under the curve, so that's an underestimate. Right? So the real area is in between these two things, using the right-hand endpoints for the heights or using the left-hand endpoints for the heights. The real area is in between these numbers somewhere, because one's an overestimate of the real area and one's an underestimate of the real area. Okay? Now let's attach mathematics to this. Okay? So in reality, we have some function. Here it is right here. Say y equals f of x. Okay? And we have some interval, a to say b. Okay? And we want to find the area underneath this function, but over this interval. Okay? The first thing we do is chop it up into subintervals over which we put our rectangles. Chopping an interval up into pieces is called partitioning the interval. So we partition the interval AB into, we'll put n rectangles in there, n subintervals in there rather, n subintervals. And we'll make each one the same width, just to keep our lives easier. Each of width, well, I'll just take the whole length of the interval, which would be b minus a, and divide it into n pieces. And each one will be that long. And we call that number the change in x. It's just b minus a over n. Okay? Okay, so what would the partition actually look like? Well, I'm going to call the first element, I'm going to call him x0. Then the next one will be x1. Then the next one will be x2, and etc. And the one before the last one will be xn minus 1. And then the nth one I'm going to call b, xn. Okay? So I'm just renaming these. Okay? So if you were to use, like in our first example, yes, the overestimate, that is, use the right-hand endpoints for your heights, it would look like this. The rectangles would look like this. So the first rectangle would use the right-hand endpoint for the height, like this. Second one used the right-hand endpoint for the height, like this, and so on. And then the last one used the right-hand endpoint for the height. Okay, and there'd be a whole bunch of rectangles in between. So here we go. So we can now estimate this area. So let's say it this way. The area under f of x, okay, from A to B will be roughly equal to adding up the areas of these rectangles. Okay? So if you look at the first one, it's f of x1 tall. See, that's f of x1 tall. And if you look at the last one, it's f of b, or f of xn tall. Yeah, you see that? Yeah. F of x1 tall. If you can't read that, draw it again. Okay, so I'm going to add it up. Lengths times widths, man. So the first one will be f of x1 times the width, change in x, or all the change in x, plus the next one will be f of x2 tall. See, right here, here's x2. That's f of x2 tall. F of x2 times the change in x, plus dot, 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 until we get to the last one. And the last one here would be f of xb, which we called xn, tall. Yeah? So 1 to n, f of x n times the change in x. Okay? Now another way to write that, because that's messy here, writing all these plus signs and dot, 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 is people compactify this. It's just a notation, that's all it is, and it's called summation notation. Since you're adding, they use a sigma symbol for sum. And realize you're summing up a figure that looks like this over and over again. So it's f of, but it's not, but these numbers keep changing down here. Here's 1, here it's 2, here it's n. These indices keep changing. So in general, it's f of xi delta x. And the I ranges here from 1 to n. So the I goes 1 to n. Okay? Okay? Now this was using the right-hand endpoint. Okay? Now let's say that. This uses, you can see all the dots are on the right here. The right-hand endpoints. The right-hand endpoints. Okay? What if we were doing it on the left? We know they both converge to the area if you do it infinitely often, because the estimates, as you saw from the pictures just a page ago, get better and better. So another way to estimate it, so I'll write or, you can estimate the area under f of x from a to b by using the left-hand endpoints. So another way to do it is the area under f of x from a to b would be roughly equal to, now if you use the lefts, then it starts at x0. and goes up to n minus 1. Okay, because you're using the left hand endpoints instead of the right. So you're not going to get this last one. The last one you get will be xn minus 1. But it'd be the same type of sum, length times width. Area of a rectangle, man. So it'd be f of x0 times the change in x plus f of x1 times the change in x plus dot 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 all the way till you get to the last one, which would be f of x n minus 1 times the change in x. And again, we can compactify this if we don't feel like writing all these plus signs and dot dot dots into summation notation. So again, it's a sum because we keep adding. These indices are changing from 0 to 1 all the way up to n minus 1. So the I will be running from 0 to n minus 1. And the figure we're adding up is f of xi times the change in x. Okay, so that's another way to do it, is using the left. So let's say that. This uses the left hand endpoints. Okay, so you could do it either way. Now let's even make up a name for this, because even this, even though it's shorter than this summation notation still is clunky. And besides, we don't have the true area here. Notice we only have estimates. You see? Estimates. The true area would be a limit of you doing this as the number of rectangles that will be n here goes towards infinity. As the estimate gets better and better, either one, left or right, will converge to the area. Okay? So let's write the actual area. Okay? So the actual area, so be careful, that's different than what I just wrote there. Actual area under F from A to B would be a limit of you doing that. So if you're using the rights, then it'd be a limit as n goes, so this is an equality, baby. N goes to infinity of that sum you wrote. Remember, on the right, I would go from 1 to n of f of xi times the change in x. But it'd also be converge if you did it on the left. Yeah, so if we do it infinitely often on the left, now here the sum goes 0 to n minus 1 of f of xi times the change in x. They both will hit the area. One from above and one from below. Remember, one's an overestimate, one's an underestimate each time. Okay, and now this gets cumbersome to write. And so now I'm going to add even yet another notation. Okay? And so we call this, well, it's an S looking figure. We put our two endpoints, one on the smaller one on the bottom, the bigger one on the top. We put the function that we were looking underneath, that was f of x, and we put a dx there. So all these are the same, and they're all the actual area. Okay? And finally, a verbal name for this. This is called the definite integral. So if you want to say it in words, it's called the definite integral of f of x from A to B. To B. Okay? Okay, so there you go. Let's do one. Now again, to do the actual area, you'd have to perform one of these limits, which can be sometimes nasty, depending on what this function is. But we can definitely perform these estimates here. Yeah? Because we can add up so many boxes. I mean, we do know how to add and multiply. So we can do either of these estimates on the right or on the left, either one. Okay, so let's do some estimates, shall we? And then give you some. Oh boy. Okay, so let's go. Let's try to give you, how about this function? How about, by the way, some people call these sums Riemann sums. Okay, let's write that. Let's go back to where they first came up and write that. These sums that we're writing here, adding up areas of rectangles, okay, lengths times widths and adding it up. Some people call these Riemann sums because his name got attached to it because I think he proved the theorem involving these. Okay? So some people call these Riemann sums. Okay? Let's put it in lights. So if you see that word, it just means add up the areas of your rectangles. If somebody says, compute the Riemann sum for this function on this interval using the left-hand endpoints, then it just means add up the areas of your rectangles using this second one here, because these use the left-hand endpoints. Yeah? Okay, let's do one. But they call them Riemann sums. They're very specialized looking sums. I mean, they are sums you're adding. Okay. So for example, let's do one. What if somebody asked you to see how much of a pane area can be? Anyway, think of somebody asked you this. Estimate the area. So again, we're just asked to estimate, not actually find the actual area. The actual area would be that limit. Let's show you again. Let's show you again, because I think you already forgot. Okay. The actual area would be performing either limit. Yeah, performing either one of these. Okay? See, the actual area. You'd have to do this infinitely often, right? And that's now being just called this notation. Okay? And in words, it's called the definite integral of f from a to b. Okay, so you need to remember these. We've just called them these things. Okay? We've just introduced this because you get tired of writing this, and then verbally we named our kid Michael. Yeah? Gave it a name, a verbal name. That's it. Okay, so now let's do one. Estimate the area under estimate the area under y equals f of x equals x squared from 1 to 3 using 4 rectangles and let's go at the right hand endpoints and the right hand endpoints. Okay? So if you draw your function to take a look at it, although the function need not really be drawn here each time, but it's good to see visually what you're doing. Okay? Here's x squared, you know it's a parabola from like high school or whatever. Here's x squared, y is f of x is x squared. Say here's 1, and say here's 3. Okay? Okay? Realize that A is equal to 1, B is equal to 3, n is equal to, he said, 4 rectangles. So 4. Okay? The change in x is b minus a over n. That's 3 minus 1 over 4. That's a half. Okay? Okay? And then you just go. Okay? So the area, so use it now. We want to use the right-hand endpoints. Okay? Let's chop the interval up. So I'm going to take the change in x here, starting at my a, and keep adding it until I hit 3. So if you add a half to 1, you get 3 halves. If you add a half to that, you get 4 halves, or 2. If you add a half to that, you get 5 halves. And if you add a half to that, you get 6 halves, or 3. Congratulations, you've just chopped the interval up into 4 equal subintervals, just by starting at one end and adding this until you hit the other. Okay? Just add this until you hit the other. Okay? The change in x. Okay? Now we're using the right-hand endpoint. So the first box looks like this. The second one looks like this. Third one looks like this. And the fourth one looks like this. Okay? And you just add it up. That's it. It's just that childish. So the area would be roughly equal to, again, it won't be equal. You can see we're getting too much. But if we put more boxes in, we still get too much, but less too much, and so on. You saw the pictures at the beginning of the video. Okay, so the first box will be f of 3 halves times the width, which is a change in x, 1 half. Second box will be f of 2, tall, times the width, a half. They're all a half in width. The next one will be f of 5 halves times the width, 1 half. And the final box will be, you can see it right here, it's f of 3 tall. So f of 3 times the width, 1 half. So we get that. Compute these. You know how to take f of something, because you know what f is. What's f? Remember, f is x squared. That's the function we're looking at. So square them things, man. So here you get 9/4 times a half plus 4 times a half. Okay, these are being multiplied. Plus 25 times 25/4 times a half plus 9 times a half. Okay, this is what our overestimate's coming to. That's equal to, I'm going to put them all over 8. Okay, this one's already over 8. It's 9/8. This one is whatever 2. I can write it as 16/8. This one is already 8, so let's smash it together. It's 25/8. And this one, it's 9 halves. Make it over 8, so 36 over 8. Multiply top and bottom by 4. And this all comes out to be 86 over 8. Reduce it, might as well. That's whatever, 43 over 4. Or if you want to get a feel for it, it's 10.75. Okay? So there's our area in square units. Okay? And that's an overestimate. Let's write that. That's an overestimate. Because we can see from the picture it's too much. Now I'm going to do it using the left-hand endpoints, and we'll see that that's an underestimate just by looking at the picture. So if I did the same thing using left-hand endpoints, okay, here's our picture. Here's our friend. Y is x squared. Y is f of x is x squared. Okay, here's say 1, here's say 3. Okay? And then we Again, same thing. A is equal to 1, B is equal to 3, N is equal to 4. The change in X is always the whole length of the interval B minus A divided by N, which is 3 minus 1 over 4, which is still a half. So nothing's changed there. Okay? Take a half and start at one end and keep adding it until you hit the other. So if you add a half to 1, you get 1 1/2 or 3 halves. Add a half to that, you get 4 halves or 2. Add a half to that, you get 5 halves. Add a half to that, you get 3. 6 over 2, which is 3. Okay, now we want to use the left-hand endpoints, okay? So the first box would look like this. Second one would look like this. Third one would look like this. And the last one would look like this. So you can see it's an underestimate now. Now we're missing area now. Last time we got too much, now we're missing some. Okay, so let's add it up. So the area using the left would be roughly equal to f of 1 times a half plus f of 3 halves times a half plus f of 2 times a half plus finally f of 5 halves times the width, length times width, which is a half for all of them. Okay, add it up. You know what f does? It squares things. Okay, so you can compute all of these things. And yawn. So that would equal 1 squared is 1, 3 halves squared is 9/4. Oops, sorry. 2 squared is 4, 5 halves squared is 25/4. I'm going to put them all over 8, because some of them have 8s. Here I get 1/2 multiplied by 4 over 4, you get 4/8. Here this is already 8s, 9/8. Here this is what? 4 over 2 multiplied by 4 over 4, 16 over 8. And finally here, this is already 8, so it's 25 over 8. Okay? So you get that? Add it all up. It adds up to 54 over 8. Or reduce it if you want. Why not? It's 27 over 4. Or if you want to get a feel for it, it's 16.75. Or sorry, 6.75. Okay, and this is an underestimate because we're missing area. Last time we were getting too much, now we're missing area. That's an underestimate. So the actual true area is in between these two numbers. 6.5 is less or equal to the actual area, and that's less or equal to our 1075. Somewhere in between those two numbers is the actual area, which requires you to do a limit of a sum to find. Okay, so we're just doing estimates right now. Okay, so with that being said, here's some problems asking you to do this. These are the problems. 4.2, boogaloo. So the problems are 4.2, number 1. Number 2. Number 4A. Number 5, A and B. Here's 4.2. Boogaloo. Be able to do them all. Okay, with that being said, I'll see you in the next video.